Look, I need to tell you something that's going to bother you. It bothered me for years. It still bothers me, if I'm being honest. You think particles have paths. You think when an electron goes from point A to point B, it travels along some definite route, like a car on a highway or a baseball flying through the air. You think you could, in principle, track it. You think there's a story about where it went. You're wrong. And I don't mean you're approximately wrong, or that it's too complicated to figure out, or that we just don't have good enough instruments yet. I mean, you are fundamentally wrong. Nature doesn't work that way. The electron doesn't have a path. It never did. It never will. And once you understand why, once you really get this deep in your bones, your entire sense of reality is going to crack open like an egg. Here's the thing that's going to sound crazy. The electron takes every path, all of them, simultaneously. The straight path, the curved path, the path that goes to the moon and back, the path that loops around your head 17 times before arriving at its destination. Every single possible path through space and time. And they all contribute to where the electron actually ends up. This isn't poetry. This isn't metaphor. This is what actually happens, and we can prove it with experiments so precise, so repeatable, so undeniable that there's no wiggle room left. The mathematics works. The predictions match reality to 12 decimal places. Nature is telling us something profound, and we'd better listen. Let me take you back to something simple. Something you think you understand. Imagine you're standing on one side of a room, and there's a wall with 2 slits in it, and behind that wall is a screen that can detect where things hit it. Now suppose you have a machine gun that fires bullets randomly toward the wall. Some bullets go through the left slit, some through the right slit, some hit the wall and don't make it through at all. What pattern do you see on the screen? Well, you get a pile of bullets behind the left slit, and another pile behind the right slit. Open only the left slit, you get one pile. Open only the right slit, you get a different pile. Open both slits, you get both piles added together. Simple. Obvious. This is how particles behave. Except it's not. Now, let's do the same experiment with light. Not bullets, but light waves. Send light toward a wall with 2 slits. What happens? You don't get 2 bright spots, you get an interference pattern. Bright and dark bands across the screen. Why? Because light is a wave. The wave goes through both slits, and on the other side, the 2 parts of the wave meet up again. Where they're in phase, where peak meets peak, you get brightness. Where they're out of phase, where peak meets trough, they cancel out and you get darkness. This is completely different from bullets. Waves do this. Particles don't. Everyone knew this 100 years ago. Light is a wave. Matter is made of particles. Different things, different rules. Then someone did the experiment with electrons. Electrons are particles, right? Tiny little bits of matter with definite mass and definite charge. So you'd expect them to behave like bullets. Send them toward 2 slits, one at a time if you want to be careful about it, and you should get 2 piles on the screen behind the slits. But that's not what happens. You get an interference pattern. Bands of light and dark. The exact same thing you get with waves. Even when you send the electrons through one at a time, so there's definitely only one electron in the apparatus at any moment, the pattern builds up. 1 dot, then another dot, then another. Seemingly random at first. But after thousands of electrons, the pattern emerges. An interference pattern. The pattern you get when something goes through both slits. Now here's where your brain starts to hurt. You might think, well, maybe the electron is somehow splitting, or maybe it's a wave that spreads out and goes through both slits. Or maybe there's some field that goes through both slits, even though the particle goes through one. So you decide to check. You set up a detector at each slit to see which one the electron actually goes through. And this is where nature plays its cruelest trick. The moment you watch, the moment you try to determine which slit the electron goes through, the interference pattern disappears. Gone. Vanished. Now you get two piles, exactly like you'd expect from bullets. The electron goes through the left slit or the right slit, and you can see which one it was, and the pattern on the screen is just what you'd expect from particles that have definite paths. But when you're not watching, when you don't try to determine which path the electron took, the interference pattern comes back. The electron acts like it went through both slits, like it took both paths, like it somehow explored every possibility. This drove people insane. Einstein hated it. God does not play dice, he said. Surely there must be some hidden variable, some deeper explanation, something we're missing that would make sense of all this. Surely the electron really does have a path, and we just can't see it. But nature doesn't care what Einstein thinks. Nature doesn't care what you think. Nature doesn't care what I think. The experiments keep giving the same answer, and the answer is clear. Particles don't have paths, not in the way you imagine them. Now let me tell you what's really going on. And I warn you, this is going to sound absurd. But it's the truth as far as we can tell. It's the best description of nature we've ever found. When an electron goes from point A to point B, it doesn't take a path. It takes every path. Every single possible path between those 2 points contributes to the final answer where the electron is. The straight path contributes. The path that curves to the left contributes. The path that goes all the way to the Andromeda galaxy and comes back contributes. Every conceivable route through space, no matter how ridiculous, has some amplitude, some contribution to the final probability. But here's the key. These contributions are not just numbers. They're complex numbers. They have magnitude A and D phase. They're like little arrows that can point in different directions. And when you add them all up, when you sum over every possible path, most of them cancel out. The path that goes to Andromeda has a phase that's almost exactly opposite to a nearby path that's slightly different, and they destroy each other. The wild, crazy paths mostly cancel among themselves. What's left? The paths that are close to the classical path, the path that you'd expect from Newton's laws, tend to have similar phases. They add instead of canceling. They reinforce each other. And that's why in everyday life, when you throw a baseball, it seems to follow one definite path. Not because it actually has a path, but because all the other paths cancel out and only the classical-looking paths survive the sum. This is path integrals. This is the picture I worked out in the 1940s, and it's one of the most beautiful and disturbing things in all of physics. You want to know the probability that an electron gets from here to there? Sum over every possible path. Give each path a phase based on the action along that path. Add them all up. Square the result. That's your probability. And it works. It works for electrons. It works for photons. It works for every quantum particle we've ever studied. It's not just correct. It's stunningly, unreasonably correct. We can calculate things like the magnetic moment of the electron to 12 decimal places, and it matches experiment to 12 decimal places. Nature is not approximately following these rules. Nature is these rules. But notice what this means. It means the electron doesn't know where it's going. It doesn't decide on a path. There is no path to decide on. The electron is fundamentally indefinite. It exists in a state of superposition, exploring all possibilities simultaneously until something forces it to declare an outcome. And that something is measurement. Observation, interaction with the environment. When you put a detector at one of the slits, you're forcing the electron to interact with the detector. You're entangling it with a macroscopic object that has an enormous number of degrees of freedom. And that interaction destroys the superposition. It forces the electron to choose whether it went through the left slit or the right slit. But it's not really choosing. What's happening is more subtle and more profound. The act of measurement splits the universe, in a sense. Or better yet, it correlates you with one particular outcome. Before you look, you exist in a superposition too, correlated with all the different possibilities. After you look, you're entangled with one outcome, and from your perspective, that's what happened. This is the measurement problem, and nobody fully understands it. We know how to calculate what happens. We can predict every experiment with perfect accuracy. But why measurement seems to cause collapse, why we only experience one outcome instead of feeling ourselves in superposition, why there's an apparent arrow of time in the quantum world, even though the fundamental equations are time reversible, these are open questions, deep questions. Questions that still keep me up at night. But here's what we do know. Particles don't have trajectories. When you're not looking at an electron, it doesn't have a position. It doesn't have a velocity. It doesn't have a path. It has a wave function, which is a description of probability amplitudes spread out through space. And those amplitudes evolve according to the Schrödinger equation, or equivalently according to the path integral formulation. Only when you measure does the electron have a position, and immediately after that measurement, if you stop watching, it spreads out again. The wave function evolves. The particle becomes indefinite once more. There is no little billiard ball traveling through space on some hidden trajectory that we just can't see. The indefiniteness is real. It's fundamental. It's built into the fabric of reality at the deepest level we can probe.
This illustrates.
Now you might ask, why does the everyday world look so definite? Why do I see a chair over there and a table over here? Why doesn't everything look like quantum mush?
Forbidden region.
The answer is decoherence. The environment is constantly measuring everything, interacting with it, entangling with it. A single photon bouncing off a dust particle is enough to collapse its position to some degree. A molecule in the air can destroy quantum coherence. The bigger the object, the more particles it contains, the more ways it can interact with its environment, the faster it decoheres. And macroscopic objects decohere so quickly in such tiny fractions of a second that they appear classical. But they're not fundamentally classical, they're quantum too. A baseball in principle has a wave function. It takes every possible path between the pitcher's hand and the catcher's mitt. But the paths are so close together and the decoherence is so fast that you never see the interference. The quantum effects are buried beneath an avalanche of environmental interaction. Still, the quantum world is there, underneath everything. And we can see it when we look carefully. We can create situations where quantum effects become visible even in relatively large systems. Superconductors, superfluids, Bose-Einstein condensates, quantum computers. These are systems where we've managed to protect the quantum coherence long enough to see truly bizarre, non-classical behavior on scales that are almost visible to the naked eye. And every single one of these systems confirms the same truth: there are no trajectories. There are only amplitudes, only probabilities, only the strange, irreducible, inescapable weirdness of quantum mechanics. Let me be very clear about something. This is not a failure of our knowledge. This is not us being ignorant about what's really going on. There have been many attempts to restore classical thinking to the quantum world. Hidden variable theories, pilot wave theories, objective collapse models. Some of them are mathematically consistent. Some of them even make the same predictions as standard quantum mechanics, at least for the experiments we've done so far. But they all pay a price. They have to give up something. Locality, or realism, or determinism, or they have to add extra structure, extra complexity, extra entities that we have no evidence for. And Occam's razor cuts deep. The simplest explanation, the one that fits all the data with the fewest assumptions, is just to take quantum mechanics at face value. Particles don't have paths. They have amplitudes. That's it. That's the world. And here's the thing that still amazes me. After all these years, this isn't just true for electrons or photons or atoms. It's true for all particles. Quarks, neutrinos, the Higgs boson. Every fundamental particle in the universe is quantum. Every one of them explores all possible paths. Every one of them exists in superposition until forced to commit to an outcome. And it's not just particles. Fields are quantum too. The electromagnetic field. The gravitational field, presumably, though we haven't figured out quantum gravity yet. Space itself might be quantum at small enough scales. Time might be quantum. Existence itself at the deepest level might be this strange superposition of possibilities, this foam of quantum fluctuations, this irreducible uncertainty. Your entire body is made of quantum particles. Right now, as you listen to this, electrons in your neurons are taking every possible path. Photons are bouncing off your retina in superpositions. The molecules in your cells are quantum objects. You are a quantum system. But you don't feel quantum. You feel definite. You feel like you have a specific position, a specific state, a specific history. Why? Because you're big. You're complicated. You're constantly interacting with your environment. You're decohering so fast that the quantum effects wash out before they can accumulate into anything noticeable. Your wave function is still there, in principle, but it's factorized into a product of classical-looking pieces by the relentless bombardment of environmental interaction. But zoom down, really zoom down to the scale of atoms, where things can be isolated, where decoherence can be slowed or prevented. There, the quantum world reveals itself in all its glory. Particles genuinely don't have paths. They genuinely take all routes. They genuinely exist in superposition. And we can use this. Quantum computers work by putting quantum bits into superposition, letting them explore all possible computational paths simultaneously, and then cleverly arranging the interference so that the wrong answers cancel out and the right answer emerges. It's a direct exploitation of the fact that particles don't have paths. They explore all paths, and we can make them interfere to give us the answer we want. This is not science fiction. This is happening right now in labs around the world. We're building machines that fundamentally rely on the pathlessness of quantum particles, and they work. So when I tell you particles don't have paths, I'm not being philosophical. I'm not being poetic. I'm describing reality as accurately as we know how to describe it. The electron going from your retina to your brain right now, carrying visual information, doesn't have a trajectory. It has a wave function. It exists in a superposition of all possible routes until something forces it to localize. And that's the universe we live in. Not the clockwork universe of Newton, where everything has a definite position and velocity at every moment. Not the comfortable universe where particles are little billiard balls bouncing around in a predetermined path. But a quantum universe where particles are probability amplitudes, where superposition is the norm, where measurement creates reality instead of revealing it. Does this bother you? It should. It bothers everyone when they first encounter it. Einstein spent the last 30 years of his life trying to find a way out of it. He failed. Not because he wasn't smart enough, but because nature doesn't provide a way out. This is how things are. But here's the beautiful part. Here's the part that makes it all worthwhile. Once you accept it, once you stop fighting it and start exploring it, you discover that quantum mechanics is not just weird. It's beautiful. The mathematics is elegant. The predictions are precise. The structure has a harmony to it that feels almost inevitable. And more than that, it works. Every piece of modern technology that relies on semiconductors, on transistors, on lasers, on atomic clocks, on GPS satellites, on medical imaging, all of it depends on quantum mechanics being correct. If particles had paths, your smartphone wouldn't work. The screen you're looking at right now wouldn't exist. The LED lights in your room wouldn't emit light. The quantum world is not some abstract theory disconnected from everyday experience. It is everyday experience. You just don't see it directly because you're too big, too warm, too constantly interacting with your environment. But it's there, underneath everything, making the world work. So the next time you turn on a light, or look at a screen, or use any electronic device, remember you're relying on the fact that electrons don't have paths. You're exploiting quantum superposition.
Quantum cosmology suggests
You're making use of the fundamental weirdness of reality. And that weirdness, that's not a bug.
The universe is
That's
a
the
constantly
feature. That's what makes the universe
branching wave
interesting. That's what makes
function.
reality richer and stranger and more wonderful than any classical story could ever be. Particles don't have paths. They never did. And now you know why. Your reality has been shattered, just like I promised. But what's left is something far more beautiful than what you started with. Welcome to the quantum universe. It's the only one we've got. And it's absolutely magnificent.